Hey everyone, and welcome back to the channel. Have you ever been in a car and someone says, "We're going fast," but then someone else corrects them and says, "Actually, our velocity is high"? Or maybe you've heard the term acceleration thrown around and wondered what it really means. It sounds complicated, but I promise it's not. Today, we're going to break down three fundamental concepts in physics: speed, velocity, and acceleration. By the end of this video, you will not only understand the difference, but also see how they describe the world in motion all around us, every single day. So buckle up and let's get moving. First up, let's talk about speed. This is the one we're all most familiar with. When you look at your car's speedometer and it reads 60 miles per hour or 100 kilometers per hour, that's your speed. Speed is simply a measure of how fast something is moving. It's a scalar quantity, which is a fancy way of saying it only tells you the magnitude, the how much. It doesn't care about the direction you're going. You could be driving 60 miles per hour north, south, east, or west, and your speed would be exactly the same. All it answers is the question, how much distance did I cover in a certain amount of time? If you run a 5-kilometer race in 30 minutes, you can calculate your average speed. It's a straightforward concept, distance divided by time. It's the number that tells you how quickly you're covering ground, plain and simple. Now let's introduce a little twist and talk about velocity. Velocity is speed's more specific cousin. While speed just tells you how fast, velocity tells you how fast and in what direction. This makes velocity a vector quantity. Vectors have both magnitude and direction. So saying you're traveling at 60 miles per hour is your speed, but saying you're traveling at 60 miles per hour north, that's your velocity. Why does this distinction matter? Imagine two cars starting at the same point. Both drive at 60 miles per hour for 1 hour. If I only tell you their speed, you have no idea where they'll end up. But if I tell you one car's velocity was 60 miles per hour north and the other's was 60 miles per hour south, you know exactly where they are relative to each other, 120 miles apart. Direction is crucial. Here is another example. If you run a lap around a 400-meter track and end up exactly where you started, your average speed might be, say, 5 meters per second. However, because you ended up back at your starting point, your overall displacement is zero, which means your average velocity for the entire lap is zero. It's a mind bender, right? Velocity cares about your final position relative to your start, not just the path you took. So we have speed, which is just how fast, and velocity, which is how fast in a specific direction. What happens when that velocity changes? That's where our third concept, acceleration, comes into play. Acceleration is the rate at which an object's velocity changes over time. Notice I said velocity, not just speed. This is the key difference. Because velocity includes both speed and direction, you can accelerate in three different ways. First, you can speed up. When you press the gas pedal in a car, your speed increases, your velocity changes, and you are accelerating. This is what most people think of as acceleration. Second, you can slow down. When you hit the brakes, your speed decreases. This change in velocity is also a form of acceleration, often called deceleration, or negative acceleration. You are still accelerating, just in the opposite direction of your motion. And third, this is the one that trips people up, you can change your direction. Imagine you're in a car driving at a constant 50 miles per hour, but you're going around a circular roundabout. Your speed isn't changing. The speedometer stays locked at 50. But because your direction is constantly changing as you turn, your velocity is changing. And if your velocity is changing, you are accelerating. That feeling of being pushed to the side of the car as you take a sharp turn, that's you experiencing acceleration. So acceleration isn't just about flooring it. It's about any change in speed or direction. Let's put it all together with a simple story. Imagine you're on a roller coaster. As the car is pulled up the first big hill, it moves at a slow, constant speed of, say, 5 miles per hour. Its speed is 5 miles per hour, and its velocity is 5 miles per hour up the incline. At the very top, for a split second, the car stops. Its speed and velocity are both zero. Then, whoosh, you plummet down the drop. Your speed rapidly increases from 0 to 70 miles per hour in just a few seconds. This is massive acceleration. You can feel it pushing you back into your seat. Your velocity is changing because your speed is increasing. Then the track curves to the left. Even if your speed stays at a constant 70 miles per hour for a moment, you are still accelerating because your direction is changing. You feel that sideways force. As the ride comes to an end, the brakes are applied. Your speed drops from 70 back down to 0. This is also acceleration or deceleration as you slow to a stop. So, on that single roller coaster ride, you've experienced changes in speed, changes in direction, and therefore constant changes in velocity and acceleration. Velocity is speed with a direction, it tells you where you're going. And acceleration is any change in that velocity, whether it's speeding up, slowing down, or just changing direction. Thinking about these concepts helps us describe motion with incredible precision. It's the language physicists, engineers, and even pilots use every day to navigate and build the world around us, from launching a rocket into space to just tossing a ball to a friend. Speed, velocity, and acceleration are always at play. So next time you're in a car, on a bike, or even just walking around a corner, think about what's happening. Is your speed constant? Is your velocity changing? Are you accelerating? You now have the tools to describe your motion like a physicist. It's a small shift in thinking, but it opens up a whole new way of seeing the dynamic world we live in. Thank you so much for joining me today to untangle these concepts. I hope this made things clearer and a little more exciting. If you found this video helpful, please give it a thumbs up and don't forget to subscribe and hit that notification bell so you don't miss our next exploration. If you have any questions or ideas for future topics, drop them in the comments below. I love hearing from you. All, until next time, stay curious.